Hi, I'm Laura. I'm going to be presenting a couple of tutorials here today on FilterNet and the layer 4 model. So I guess over the first day and then now, a lot of the first day is like learning how to use BMTK, build your models, figure out like what the cell models mean, and we're like slowly building towards making like a large. Oh, can you?
Sorry, I feel like here at the back of the room we can barely hear you.
Oh, okay, I can be louder.
But it was just like, yeah.
Okay, all right, yeah. Sorry, didn't realize. Sorry, I think I just didn't realize I was used to the smaller room. I can try and.
Yeah, maybe just project.
Yeah. Okay. All right. So to reiterate, we're slowly building towards making larger scale models of Cortex here. So taking like the building blocks and components from yesterday, now we're going to go over how to make like input, realistic input for a protocol model, and then lead into a layer 4, a model of the layer 4 of the visual system. And then after that, we have an optional tutorial where we're going to try and use a software from one of our collaborators to run the full-scale V1 model. We do this because it's such a large model that we can't really run it in a notebook. So we'll just take like a couple minutes. I don't have a whiteboard. But if you guys, let's see, where's, 1 second. Okay, I'll just use one tab. But if you guys can. Oh, sorry. Okay. Oh, you can't see my screen. Okay. Another second. Okay, but if you can go to the website cybershuttle.org and then click like login. And it might be different on your computer than mine. But if you can make an account, you can either use, for the most cases we've checked, an institute login should work. So if you clicked on like select an identity provider, your institute like should be there. If it's not, you can also use a Gmail account to make an account. And this will just give you access to the resources on Cyber Shuttle, which I'll explain in a moment. But if you just take like 5 minutes. I use my Gmail email, so that's kind of what I do. Sorry, and if the email address isn't showing, sorry, the website, it's cybershuttle.org. Maybe I could pull the whiteboard over. That's fine. Okay, all right. Have we tried? Is like the login working? Or okay, cool. And then we'll move on. It'll make sense at the end. Okay. All right, so to go over tutorial of 5, we're going to be, explaining the FilterNet model in BMTK. For some context, when you're making a model, you need to provide some sort of input to your model. And like the type of input kind of depends on what you're trying to do. And there are many options, and you can provide random input. There are options in BMTK to provide spiking activity of neurons like from experimental data. And we'll go over some of these options like in later tutorials. But another option is to provide some sort of like structured spikes based on our idea of what like other brain regions are doing or what the input should look like. And one option we've made here is a linear nonlinear Poisson model that like approximates what the visual system is doing. So the input from the retina to the thalamus to V1. And it's some sort of like graphic. Essentially what this does is you provide like an image to the model, and it processes it in a couple different steps, a spatial temporal filter. That input goes through a nonlinear transformation and to estimate the firing rate of these neurons. And then you run through a Poisson spike generator to generate like binary spikes instead of a firing rates. And this is the input you can provide to a model. This model was developed by many different people, but is like mainly attributed to Eros Simoncelli's group in a paper by Jonathan Pillow back in 2004. It's essentially a GLM, depending on the nonlinearity used, but in most cases it's a GLM, which means that it's really easy to fit this model to data. And so that's convenient for what we're doing here, if you want to generate input spikes that approximate like what the thalamus is doing. Okay. And then some common settings you'll find, or like things you like want to know when using this FilterNet model. The frame rate is really important. In the default setting in the model is 1,000 frames per second, and this is important, even though it seems really high, because the like temporal properties of the thalamic cells or cells in the LGN are like very precise temporally. And so you can kind of like notice here that if you use like a 250 hertz frame rate versus like 1,000 hertz, you'll kind of like, an aside, you'll get like much faster performance, but you're missing a little bit of, is there a cursor? Okay. A little bit of like temporal fidelity. So that's just like something to know. Okay. We have a few other like input options for FilterNet. Like I mentioned, it's designed so you can take like any image and then it'll process the image and provide some sort of spikes. So the easiest, or like the option with the most flexibility, is to provide some sort of like movie as an input to your model, and this is just a NumPy matrix. But we also have designed a couple like built-in stimuli, so it's a little more convenient for you. The one we use the most is a drifting grating. These are one of the most like popular stimulus options in vision research. But there's also a field flash or like a looming spot, and it's like known that some cells in V1 are responsive to these types of stimuli. Okay, and then also like all of these details are on the BMT website, and I think many are also noted in the tutorial. So all of this information is available to you, and you'll also have the slides later. But again, just like so you know, every stimulus option has a few like different settings you need to provide. It's, I think, fairly intuitive, kind of like when you want the stimulus to start and stop, and like the intensity, for example. And then for the drifting grating, you need like a few other options. So to specify like the angle of the grating, like the frequency, like et cetera. Okay. The workflow of this tutorial, if you haven't looked at it yet, is you want to build a model for like to take the input from the FilterNet. That was done in previous chapters. And then the other thing you need to do to make FilterNet work is fit it to data. But we've already done this for you. Just like for some background information, the FilterNet model, or all of the LGN neurons, were fit to data from Piscopo et al. And Durand et al. A few years ago. And so they should behave, or they behave, you know, to our best estimate, the way LGN neurons should filter image data. And so that's already done. And then all you have to do in the rest of the tutorial is prepare the stimulus you're interested in providing to the network, run FilterNet, and then the output would be in Sonata spike file, which was explained like yesterday. And this is the same spike or like file output that the other models run as well, so it's kind of easily transferable. And you can provide this to your network or your V1-like network as input. Okay, a few more details. There are a lot of details in all of our models, but just to go over what you're going to be editing to tell FilterNet like what to do. This is an overview of the configuration file. You'll notice it's pretty similar to the configuration files for like the other models you would have worked with yesterday. There are some like common themes. So one is telling the simulator like where to find the components for the model and the network, and then where to like put the output of the model. But it's important to know so that you know like where to find your like simulation results like after you're done running the simulation. Here it's in the inputs folder. The target simulator will be the LGN model. You start at 0 seconds, you run for 3,000 milliseconds, so the units here are milliseconds. So it's 3 seconds. Components are in the filter models folder. And here are the output settings. You want a log file. You want it to be in the output directory. And then there are two possible outputs for the model. One is spikes, which is what we want to feed into the next model. There's also like a rates option. And And these files are fairly large, but it's useful for like diagnosing if the model's working properly. And as another side note, this spikes file can be either in H5 or CSV format. It's up to you what you want to use. The trade-off is that like the H5 format is more efficient, so it'll be a smaller file, but it's like a little more work to read out. So 2 options. Okay, and then probably like the most work for this section is editing the inputs section here. And so what you want the input to the model to be. For this example, it's the input type is movie, and the module is a full field flash. It's gonna just flash a screen to the model. The size of the input, the time goes on and off, so it's like from 1 second to 2 seconds. Intensity and the frame rate, which is 1,000, as we talked about. All right, and then where to find the network files. So these are the LGN nodes that were pre-made and should already be in your folders. There are some other options in the tutorial to create movie files from images. So like I mentioned, you can make your own movies, and it's just like a NumPy matrix, like time by row times column. But there are some like pre-made movies or image stimuli that we have available, and these are the same stimuli that were shown in the Allen Brain Observatory experiments. And so if you like want to compare like your model to like neuropixel or calcium imaging data like from the mouse visual cortex, you can also like use these stimuli. This is just natural images. They flash or change every 250 milliseconds. And the second option is the movie Touch of Evil. And it's the original frame rate is like 30 frames per second. And so what you have to do is like upsample it so that there are 1,000 frames per second. All right. Okay. And then at the end of the tutorial, there's an optional, like I guess, exercise to, instead of driving like the point net with this model, to drive like a biphysical model with the spikes from the FilterNet. And so if you want to like move your files over from like yesterday's tutorials and try running the model with FilterNet and like compare the results, that's an option. And probably like a good way to test your understanding. Okay, are there any questions about FilterNet so far? Can everyone hear me? I probably like stopped projecting over. Cool, all right. So that's that. Have fun. And then this was a new option developed last year, where if instead you want to provide like auditory stimuli, so this is like one-dimensional input instead of like a 2D image, and stimulate input to like the auditory cortex instead, we developed an auditory FilterNet, or this was developed by Ping, I believe. It works in another department now. And what it does is instead of convolving with like the spatial temporal picture filters directly from the signal, it first generates like a cochleogram from the one-dimensional auditory input. And so that's like frequency versus amplitude, I believe, in the signal, and then does the same thing. So you can provide some sort of input to like an auditory like network. And the online tutorial, it's not part of like this workshop, but we have information on that like on the website if you're interested later. Cool, all right. Any questions about all of that? All right, 1 second. Okay, so I think in yesterday's tutorial, there's like a simplified layer 4 model. What we're doing in this tutorial is to make a much more detailed version of the layer 4 model that's very similar to the full cortical column model that we use for our scientific research. And like one of the reasons we do it this way, because we can actually like run this in a Jupyter notebook. It's like small enough that it still works, but then you also still have all the detail that you might want. And so you can kind of like generalize to understand what the full cortical column is doing. All right, so it's going to cover how to build like a network model using multiple cell types, how to connect realistic input patterns to the model. So this is like the FilterNet we just talked about, how to manipulate the inputs to see different network behavior, and how to make like runtime changes to the network to explore parameters without having to like rebuild the model. So that's very useful and saves a lot of time. It won't cover how to create individual cell models because we kind of talked about that in previous tutorials. And it also won't teach how to decide on network parameters because it's like a little bit up to you. It also can take some time and be finicky. So, right. This is like, if you've looked at it already, this is a really long tutorial. So the way it's formatted is there's like one main tutorial, number 6, and the first few sections are connected, is linking to like 3 mini tutorials like over each step of building the model. So one is like building the V1 network, or the V1 layer 4 network, the LGN model, and the background input network. The second is making the input spikes, and then the third is like connecting everything together and making sure the parameters are like reasonable, so you get reasonable behavior. And then once all of that's done, you run the model and you analyze the results. And then there are a couple other sections that go over how to modify the synaptic rules, so you get more realistic looking results, or you can perform different experiments on the fly, and then adding external inputs to the network. Okay. So like the other tutorials, all of our individual cell models come from the Allen cell types database at this link here. Hopefully you've all had a time to like explore this by now and kind of play around a little bit. But that's where we're getting all of our individual cell models that go into the larger scale network model. Okay. And now instead of, to clarify more of like how we're using the FilterNet model, we have a full scale LGN model. And what this does is it covers a 240 by 120 degree visual field. There are 4 different cell types to cover all the different types of cells we find in the LGN. And they're shown on the right here. And so what this is the sustained on cells, sustained off cells, transient off cells, and then on-off type cells. And you need like all of these cells to, and their connectivity and spatial profile to like generate like direction selectivity in V1. So we'll go over that in a second. There are about 17,000 total neurons, and all of these cells are mapped spatially so that their like position in space corresponds to like their what's the word? Like their tuning curve, like where they respond to in space. Okay. All right, so as a side note, like how this works is that you need the sustained on and transient on cells to generate tuning selectivity in a V1 network. And so they're arranged so that your sustained on cells will be in a strip next to the transient on cells, and both of these cells or groups of cells connect to like a single or a population of V1 neurons. The sustained on cells have a very long time scale of like activation and then slowly turning off, while the transient on cells have a much faster time course. And so what happens is that if you have, these cells are both responsive to like a bar, for example, some sort of like oriented stimuli. And so what happens is if the bar moves in like one direction so that the sustained on cell is activated first and then the transient on cell, the input to the V1 neuron will kind of like look like this, so they sum together. The input's like super threshold, and the V1 neuron spikes in response to the bar moving in that direction. But if the bar is moving in the opposite direction, so that the transient on cell spikes first before the sustained on cell, the inputs don't sum together, and so you don't get a response in that direction in the V1 neuron. Right, so that's kind of like how, theoretically, the direction selectivity comes to play in the V1 model. Okay. As like another note, there we have additional input to the V1 network, and this is meant to make up for like all the inputs from other cortical regions or like subcortical regions that would come into V1 aside from the thalamus. We do this in a pretty like straightforward way with like very few assumptions, or I guess many assumptions, with a single background unit with like different weights to every neuron type, and this is sort of like calibrated to what we want the firing rate of those cell types to be. So it helps adjust the overall firing rate, and it's like another source of noise in the model. Okay, and then so that's building the model. What this is doing is providing a way to adjust the weights, like when you're running the model. You notice in like a lot of our models, we define the weights at the beginning when we're building the model, and then it's not always intuitive to know like how you would change them afterwards if you want to. And so without like knowing to do this, you would often have to rebuild your model, which can be incredibly time consuming and we don't want to do. And this also gives you a little more flexibility. So the way this works, and you'll see it like in the tutorial, is that in the edge types file, there's a column that says synaptic weights. And in that file for each connection type, you'll say the name of the function. So this would be direction rule others. And then in the run.net.py file, you'll see this code with the @synaptic weight decorator like before the function. And what this does is it tells the model when it's simulating the model to change the weights for that edge type according to these rules. And we use it here to implement like a like-to-like connectivity in the model. So this was it's known that in V1, cells that have similar tuning selectivity also have stronger weights between them. And so then this code for each edge type, it calculates like the tuning difference and then like adjusts the weights accordingly. So that cells that have more similar tuning direction also have like stronger connectivity weights. And so the strength or like the function here is plotted on the right, and the code is here. And you can like adjust it if you're interested, see what happens. It's kind of fun. Okay, and then like as another like aside, if you're running an experiment, you typically want more than like 3 seconds of data. You would want like a couple hours to like multiple days, right? Where you like run multiple trials at multiple directions and like aggregate your data and like calculate statistics from there. Just like for the sake of convenience for like this notebook, we're just running like one trial. And so I think it's like a trial at a drifting grading of 90 degrees. And then just like, so we can like quickly assess the output of our model. This is what the analysis plot is going to be, where we're plotting the firing rate of each neuron versus the tuning angle. And what you can see is that there's like a little hump here at 90 degrees. So these cells are a little more responsive to the drifting grading than the other cells. Okay. Are there any questions so far about this model? Cool, all right. And so that's like a brief overview of what the tutorial will be. And like, please ask questions like while you're going through things. The next few slides are just kind of like general like organization tips and kind of like helpful hints for like how to do like large scale modeling. So I don't know if I mentioned, but these slides were originally prepared by Shinya, who does a lot of the work with the V1 model. And so these are like kind of things he finds helpful and or wanted you to know. I also think they're important. Okay. So some kind of like things to know when you're working with large models is that there are a lot of steps. As you can see, there are like 4 tutorials here. So it's helpful at some point if you have a workflow going, you want to make some changes and then run the same thing over again, to start using some sort of workflow manager like NewMake or SnakeMake. And what this does is you can list all the commands you want to run, what the input file should be, what the output file should look like. And so if you make some sort of change, you can run a single line of code and it will like check what files are missing and like remake everything for you. And so that's useful because it saves a lot of time and a lot of brain power, and also good for like scientific replicability, so that you can make sure you're like doing the same thing every time. So that's, I think, a very useful tip. And another thing is that when running these large models, because we're doing so much like every second, there's so many equations involved, they often take a long time. And so what you would want to do at some point is start using like some sort of parallelization. These models, they all work with MPI, which is like the preferred, what we prefer to recommend using here, which helps you scale the computation across multiple CPUs or computers. One note is that PointNet, because we're using a backend of Nest, it requires like recompiling in a very specific way. Just like so you know, that can be tricky. And if it's like not working for you, we'd recommend using like OpenMP instead, which won't be as fast or won't help on a cluster, but will still improve computation speed. And you'll have these like slides afterwards, but these are like the commands you would use to run BMTK like with MPI, for example. Instead of writing like Python, then the script name, you write MPI and then like the number of cores you would want to use. And then if you need to use like OpenMP, what you would do here is edit the config file under the run section. So you like specify the number of threads. Okay. And then every step of these like model building has been published at some point. And so if you want more information on like anything here, or want to know more of the details, you can like check out all of these papers. All of the original cell models were fit from these papers by Gowans and Crane-Teeter. And then the layer 4 model was published in Arkhipov et al. In 2018, and the like full V1 column model that we're going to go over in a second is this paper here by Belair et al. With software by Kale. Are there any questions at this point? Cool. All right. Let me just check if I've. Okay. So if you signed up for Cyber Shuttle, I think you should have access now. So we'll go over that like in a second. All right. So that's how, if you're interested, you can start to like test out and run the full V1 cortical column model. This is all optional because it is like a little bit experimental. But basically what we've done here is that we've collaborated with Cyber Shuttle, which is a way to connect like research notebooks or like a Jupyter notebook with like data sets and then compute resources like all online. So then the idea here is like if you want to run the V1 model, for example, but you don't have like a powerful enough like desktop, you could use like Cyber Shuttle and it'll connect you to the resources you would need to run the V1 notebook or the V1 full cortical column model. There are a couple of different options. Like you can, for today, like it'll be free, but you can like purchase like AWS compute resources, and there are also ways to get compute resources like through grants with NSF, or there are some like free resources available too. So these are just like different options, and it's convenient for us like to run this workshop. Okay, all of the details for this, and I'll go over this like in a second, are on the cybershuttle.org like website. And we have like an FAQ and user instructions like on the events page. And it's linked right here under the 2025 Allen Institute workshop. Okay. And I think these instructions should also be, I think they're included in the exercise section on your Jupyter notebooks, where it says like V1 cortical column model. Okay. And I'll run, we have quite a bit of time left, so I'll do kind of like a tutorial after. But for some like overview of how this works, it'll cover how to like access and run the V1 cortical column model from the Belair et al. 2020 paper, recreate some of the main results from the paper, how to manipulate the input to see different network behavior, and how to scale the manipulation so it can run multiple, like a range of simulations like one after the other, instead of like having to like set up each simulation one at a time. It won't go over like how to run FilterNet again, since we already did that, or how to build a model from scratch. One of the reasons is that it would take a really long time to build the model. It takes, like on my own computer, it takes like sometimes like 8 hours, something like that. So we're not doing that. It's already provided for you here. And we'll just like run it and see if we can do any sort of science with it. Okay, so the V1 cortical column model was published back in 2020 in this paper here. And what it is, it's, we provide visual input to our LGN model. This is FilterNet. And the model consists of like all 6 or 5 layers of cortex instead of just the layer 4 model, and builds up out of our best estimate of the cell type makeup in V1 and the connectivity between layers. This is some other thing to know is that this is like a 400 micron radius cortical column. And because we have like such specific like spatial connectivity in our models, what we need to do on top of this to avoid like boundary effects at the edge of the column is to include an additional like ring of neurons like outside the 400 micron radius. So that's what you see in the figure here on the right. So what you end up with is about, I think, 800 microns in radius and like 260,000 neurons. So this is a fairly large model and takes quite a bit of compute resources to run. And then another thing you'll note in the code is that it'll specify like when you're running the analysis, you need to reduce the output file to just like the neurons like within the 400 microns of the center, because otherwise you'll be analyzing these neurons like on the edge that like don't have as much input as the neurons in the center. Okay. And then the output we're trying to recreate here is figure 7 from the paper. We provide a drift and grading. We can compute the firing rates of each neuron and the direction selectivity. As well as figure 8, so we can provide like different types of stimuli to the model. And what you can see is that, for example, in response to the full field flash, you don't get any sort of like overrun excitation behavior. The model still behaves normally, and it also behaves like realistically in response to like natural movie stimuli. Okay. To go over the workflow of the tutorial, this is a schematic of how we, in general, like recommend to build your model. So you would build your model, like run analysis, and then analyze the data. And then in between, you're using your Sonata network files or like configuration files to control what the simulation is doing. For this tutorial, the model's already built. And so what we're doing instead is we make edits to like the configuration file to change what we want the model to do or tell it to do something different. Okay, so to go over what the configuration file looks like again, it's pretty similar to the other files you've seen, or the FilterNet configuration file. I'll point out where to find it once we go over the Cyber Shadow tutorial. But similar to before, in the beginning, you tell the model where to find all of the important components or folders in the model and where the output would go. That's all in this first section. We have our runtime parameters, and so the duration of the simulation, 3,000 milliseconds again, and the time step. So here the time step's a little bit larger because to make it like more feasible because we're running so many neurons at once. We have the file that'll tell you where to find the spikes from the LGN or your FilterNet results. And so for all of these tutorials, we've pre-run the FilterNet network because it just like kind of speeds things up a little bit. And instead, the output from FilterNet will be like located in different output folders, so you can just like provide it to your model without having to run the network itself. It'll be a little bit faster. And for the most part, this is what you're editing in each of the tutorials. Like the different like inputs you're providing to the model. Okay, where you'll find the background spikes, and then the format and like location of the output. And so here what we want is like the spikes file again. The components, so where you'd find all the cell models, and where you find the locations of each of the like network files for the models, which are already like pre-built, so you don't like really have to worry about it. Okay, and all the edges. As a side note, like if you want to, instead of using Cyber Shuttle, like run the model yourself on your own desktop like later on, we would recommend using like a fairly powerful workstation. It doesn't usually work on a laptop. But what you would want to do is kind of like look at the way this is all set up here, and then make sure that when you like download the network files for the V1 cortical column model, like set it up the same way. So it matches the configuration file and like the way things are set up in the Cyber Shuttle notebook. So if that like, hopefully that like gives some like hints to like how you'd want to do this on your own. Okay, and then we'll run the simulation. We'll get an output that looks very similar to the paper. And what you can see is that this was in response to, I think, a 270-degree drift and grading. So you can see that, some cells are more responsive than others to this stimuli. And then after that, there'll be a few different like example use cases or options for what you can do with the model. These are also listed in the tutorial of like things you can try and do with the model is it can be really useful for generating like sample data. If you want like a lot of like input from like V1 or like data from V1, but you don't want to run like hours of experiments or don't have like access to that, you can use this V1 model instead. And people have done that before. You can run perturbations experiments, so testing the role of different cell types in the model by perturbing their activity, test responses to different like visual stimuli, or use it to, like I find it also really useful to check your like understanding of how V1 is like built, because it's really helpful to like there's this saying like if you can like build it, then you know it. So just by like the process of going through all of this, you probably have to like think about each step more than you like normally would when you're like running an experiment. Okay, thanks. And then in the next 20, I think I have 20 more minutes. Are there any questions from here? So I'm just going to show you guys how to use Cyber Shuttle. The instructions should be on the website as well. But just so that you have some demonstration. Okay. You'll want to log in using like the same credentials you used to sign in. This is taking a moment. Okay. And then once you're on Cyber Shuttle, you can go to the, well, I guess to show you again, all of the instructions are on the advanced page and should be linked in your folders. But you can find the instructions for how to run all of this here and what Cyber Shuttle is. And then like some FAQs as well if you have any questions. Also just like email me or feel free to like email them directly. But once you've looked through all of that, you can go to the catalog and find our notebook by, you can scroll through. Specifically, you'll find it by typing Alan. Just Alan works best. No, this isn't. Alan AI, and it's this one here, Biorealistic Multi-Scale Simulations of Cortical Circuits. And you want the one labeled repository, not dataset. So the dataset contains like the V1 network model, but not the code to run it. And then you'll click Start Project section and create session. And it'll take just like a few moments to connect to resources. As some like background information, I mentioned you can run the notebook or like run resources here 2 ways. One is using like resources from like AWS. So we have like a bit of like a short example on how to do that at the beginning. And then the second half is running the V1 cortical column model. And then we switched to using a different cluster for that. It's called Anvil because we need like more resources than we could get on AWS. What the code also does, it gives you like 1 hour of compute time like at a time. And the notebook takes probably like 3 hours to run. But the way it's set up is each section can run independently. And so if you can run like one at a time and kind of like pick and choose like what you're interested in doing. Right. Just thought it was like a little more useful to provide more information than less. And so that's what we're doing here. Okay. So it brings you to Jupyter Lab. And then the notebook is linked here, V1 notebook. If you're interested in looking at like the config file I went through, it's under like V1 point config. And you can find that all here if you like want to look through what's going on. Okay, and the like file structure is the way you would like want it to be set up to run the model. Okay, we're going to, so like I mentioned, like the first section is like a mini tutorial to test out the resources. Maybe we'll skip that for now. It's just a miniature version of the layer 4 model. And instead, okay, we need to run the first block of the notebook. And what that does is connect to the Cyber Shuttle resources. There's just like one more thing to know, because it will ask you to like click a link to like authenticate that you're a real person at one point. And it will just take a moment. Okay, so then all you do is click on it, and then you can close that tab, and everything else should run. Okay, so you can scroll down to like, if you want, or you can like also go through the rest of the notebook if you want to. And then run the rest of the V1 model notebook here. Okay, and what it does is it requests resources from an external source, so that does take some time to like connect to the resource, the same way it might take some time to like, if you're used to using like the cluster, at your institute. Sometimes it takes a little bit of time until the resources are available. So that kind of is what happens here. But once that's set up, you can run the rest of the notebook. Yeah. Are there any questions at this point? Okay. We can do like a 10-minute break before the next talk, if that's, yeah? Okay. Oh, sorry, one other point. After you're done using the notebook, it's like polite to run this last block of code. And what this will do is it stops the runtime. And so if you don't end up using like the entire hour of resources, you'd want to like run this block of code here so that it like gives it back. So you're not like hogging more resources than you need. So that's like a good thing to do. And then another thing to be aware of is that we started a session here to run the notebook. What you can do afterwards is go back to your session. I have a couple here because I've been testing things. And any changes you made during that session will be like saved in your notebook. So you can go back over like months or whatever. Do your science, like run something, run an experiment, come back, and it will all be there. You can download the files so you have all your simulation output. But if you're like really done with it, again, just to be polite, you should like terminate your session. So that, and then like, you have to click the trash bin too. Just so that you're not using more resources than you need. Okay, I think that's it now.